Welcome back, students. We'll resume and we'll continue the same thing, that is polysaccharide, and we have completed two candidate structural homopolysaccharide. Then we'll go for two structural, storage polysaccharides, homopolysaccharide. One of them is very famous, starch. It is very famous, but students are often confused with this. Starch in as such is not a single molecule. It is a mixture of two molecules. It is a mixture of two molecules. One is amylose and amylopectin. Depending upon various sources, amylose is found from 10 to 30% in starch, and this will be some 70 to 90%. Most of them are the amylopectin. So amylose is also a polymer of glucose, homopolymer of glucose. And this is also a homopolymer of glucose. Then where is the difference? And that too, it is also alpha glucose, alpha D glucose. Here also alpha D glucose. But the difference is that this is linear and this is branched. This is branched. So that is linear and this is branched. So something we have already discussed the structure of the amylose. Just imagine amylose units are connected with one another. Then we will get these, we have studied about the maltose. When maltose units are joined together, we get the amylose. So it will be just a continuation of the same structure which we have already discussed. I need not draw it anymore. Alpha 1,4. So it will be like this. So like this, it continues. It will continue like this. That makes our amylose chain. Now when it is amylopectin, we will find that about some 12 to 30 residues after, we will find a branch point. A branch point will be there. A branch point means we will find here what happens? Every glucose molecule is joined, one glucose molecule this side, another glucose molecule that side. But at a branch point, a glucose molecule will be joined with 3 glucose units. It is like this. At the branch point, if I am writing hydroxyl group at the third position at the top, it indicates I am speaking about the glucose. I need not write all. So this is the continuing chain. So this is the continuing chain. I will just show you what is the meaning of a branch point. So here we have the branch point. In case of amylopectin, structure is rather like this. So this is the branch, this glucose unit, just mark this one. This is joined to one glucose this side, one glucose that side, and one is here. Here with 1,4, here with 1,4, here with 1,6. This is alpha 1,6 glycosidic linkage, and this one is alpha 1,4 glycosidic linkage, and this is alpha 1,4 glycosidic linkage. So this is what we find the structure in case of the amylopectin. Now you have a very common knowledge about this starch. It has been taught to you in the school in itself that when you have the starch solution, add a drop of iodine, then it will turn blue, inky blue color. The solution will become inky blue in color. So how it happens? It happens mostly due to amylose present in it, because amylose remains in a helical structure. When we make a solution, this amylose makes a helical, it will be in helical structure, and iodine will be trapped inside this helix. Iodine will be trapped inside this helix, giving an or imparting a blue color. Amylopectin on the other hand, will produce a red-violet color solution, because amylopectin produces, instead of helical chains or helical structure, they will produce a micellar structure, means globular or micellar structure. So that will produce a violet color or a red-violet color, something like that there will be. So the major difference when we think about this amylose and amylopectin is one is branched, another is unbranched. This is the most important thing. And second thing is that if we test it chemically, their presence, amylose will produce the blue color when added with iodine solution. Same iodine solution will yield red-violet color in case of the amylopectin. And when it comes to the digestion, amylase can digest amylose easily. Now amylopectin will be partially digested using the amylase. Then there must be one branch removing enzyme. There must be one branch removing enzyme which will translocate the branch to another point, make it straight. Then only we will again find this modified amylopectin can be acted upon by the amylase, or else this only pure amylase cannot digest it completely, will digest it only partially. So another storage molecule, one more thing, this starch is found in plant. Starch is found in plants. Now another one is glycogen, homopolysaccharide. This is a homopolysaccharide. This is branched. Branched like who? Which one? Amylopectin. Then what is the difference? Difference is that it is rather more branched. More branched than amylopectin. It is more branched than amylopectin. It also yields red-violet color when added with iodine. But another difference is that we find it as the storage molecule, storage polysaccharide in animals. And we find also it to be found in fungi. In animals and fungi, this glycogen is used as the storage form of the polysaccharide. They store glucose. Whenever we take more carbohydrate, we digest it in our alimentary canal. Glucose is taken to the bloodstream, and in the bloodstream glucose level goes high, then we know that glucose level cannot be maintained very high in the blood. So they will be driven into the cell by the action of a hormone called insulin. Then insulin will help converting these glucose inside the cell, particularly in the liver and muscle, into glycogen. So it will remain there as glycogen, this glucose. Glucose will be first converted to glucose 1,6-phosphate, then 1-phosphate, then it will be it will be added to an existing glycogen chain. It will be added to that, such that the glycogen size will keep on increasing. And whenever we need, when we consume the glucose present inside the blood, then glucagon hormone will act upon, and these glucose units stored in the glycogen will be gradually liberated, and they will be constantly supplied to the blood. So that is all about the storage polysaccharides. So thus we have seen 4 candidate molecules. 4 candidate molecules. One was cellulose, another was chitin. Cellulose was, these are structural, but all are homopolysaccharide. Then we have this amylose, amylopectin, amylose, amylopectin, and glycogen. Cellulose was found in case of plant, chitin was found in case of fungi, and certain arthropoda exoskeleton, and arthropoda exoskeleton. Now amylose, amylopectin, they are also found in plants, and glycogen is found in fungi and animals. So that is all about it. And another thing we can go for, that is dextran. Dextran is also another polysaccharide. This candidate I was just discussing, that is alpha 1,6 will find, that is the D-glucose, dextran. D-glucose linkage is alpha 1,6, but it is branched. And this branch point can be either alpha 1,2 or alpha 1,3, or it can be even alpha 1,4. So 1,2, 1,3 and 1,4 we can find them to be present, and they are mostly found in yeast and bacteria. They are found in yeast and bacteria. Found in yeast and bacteria. So that is all about the homopolysaccharide. Then we can go for the heteropolysaccharide. From among heteropolysaccharide, I will go for, we will just have some kind of one category we call mucilase. Mucilase, they store water, they provide lubrication and protect injuries in case of plant. You might have marked that whenever there is a puncture or you make some injury in a plant, they produce a kind of liquid oozes out, and sometimes that say you just try to remember about the lady's finger, bhindi. Bhindi, you know that how mucilase it is. That is the function of one heteropolysaccharide present in them along with certain protein molecules. Then we have another, that is heparin. I will come to their structure. That is heparin. It is an anticoagulant found in the produced by the mast cell. This is anticoagulant. Produced by mast cell of connective tissue. mast cell of the connective tissue. Then hyaluronic acid. Hyaluronic. Then hyaluronic acid, we find it is the ground substance of many connective tissues, many connective tissue. Then in the synovial joint, we also find them. In the joint, synovial fluid of the joint, we find them. Next is your chondroitin sulfate. Chondroitin sulfate, then dermatan sulfate, then keratin, so these are the things present, and finally we can have another one, that is the murin. It is found in the bacteria cell wall. Now keratin sulfate, dermatan sulfate, they are found in the skin. It is found in the cartilage. It is the ground substance of many connective tissue. Connective tissue, then synovial fluid, and so on. We will just see some of their monosaccharide units. They are heteropolysaccharide, means at least two kinds of monosaccharides will be there. We will first see chondroitin sulfate. Let's see the chondroitin sulfate. Chondroitin sulfate, there are two. One is D-glucuronate. D-glucuronate, and to this there will be N-acetyl D-galactosamine 4-sulfate. N-acetyl D-galactosamine 4-sulfate. So what is the linkage? The linkage will be beta 1,3. These two are joined by, this linkage is beta 1,3. Acha. Now you can imagine that there will be another N-acetyl D-galactosamine 4-sulfate. So N-acetyl. So this linkage will be not same as the beta 1,3. That will be beta 1,4. So glucuronate is joined to N-acetyl D-galactosamine 4-sulfate with beta 1,3 linkage, and whereas with this it is beta 1,4 linkage. So that will be joined to this with beta 1,4 linkage. Now I will just draw one such structure. All the structure I am not drawing, just for your convenience I will just show you one structure. Now what happens? Glucuronate. Do you recall the structure of glucuronate? Glucuronate means this will be sixth position, there will be COO minus. Instead of CH2OH, it will be COOH, or we can put it COO minus. This is beta, so we will put it beta, make it beta. So this is your D-glucuronate. This is D-glucuronate. The next one is N-acetyl D-galactosamine. N-acetyl D-galactosamine 4-sulfate. So let us draw it first. First of all, we will draw the galactosamine. The name appears to be long, but when it is long, it also describes what is what. So you just see it is galactose. So we put it galactose. Galactose, I have told you that this is on the third and fourth hydroxyl group will be at the top, third and fourth. Now it is N-acetyl, so at the second carbon atom, NH, C double bond O, CH3. So CH3, C double bond O, NH. So this is your N-acetyl, N-acetyl, then this is galactosamine. Now so this is again beta, so OH is here. Now 4-sulfate. So carbon atom 1, 2, 3, 4, at the 4 there will be the sulfate group will be there. So we can put it sulfate group. We can put it. Now, so we will have this. Next thing is that we put it SO4, 2 minus. Now we will have this. Our important point is this beta 1,3. Beta 1,3 glycosidic linkage. So how this beta 1,3 will be there? So this is the 1 and this is the 3. So we will have the linkage like this. We can write it anyway. So beta 1,3. And when it comes to this side, the other side, this is beta 1,4. So the same structure we will have 1. It is OH. So we will have this. Where is it? So this is our beta 1,4 linkage. This is our beta 1,4 linkage. So at one side one kind of linkage, at the other side another kind of linkage. Similarly, we can have, so this is our chondroitin sulfate. Chondroitin 4-sulfate. We can have the heparin. We will have the heparin. In heparin we have glucuronate 2-sulfate. This glucuronate 2-sulfate, I think that it is easily understood what will happen. At the second carbon atom, we will have this sulfate group to be present. That means if we are drawing it like this is the second carbon atom, we will have the sulfate group here. So this is what it means. Then another one is the D-glucosamine 6-sulfate, N-acetyl D-glucosamine 6-sulfate, N-sulfo D-glucosamine 6-sulfate. Well, so this N-sulfo D-glucosamine 6-sulfate, it is what? The structure is interesting. First N, then with this N-sulfate group is joined. So that is important here. Then here also 6-sulfate, CH2 sulfate is there. Then other things are as usual. Other things will be as usual. So these two will be joined. These two will be joined using beta 1,4 linkage, alpha 1,4 linkage. There will be alpha 1,4 linkage and alpha 1,4 linkage, both sides. This side also alpha 1,4, this side also alpha 1,4. So this side alpha 1,4, and here also this linkage is also alpha 1,4. So this is the heparin. This is the heparin. Similarly, we can have the chondroitin 6 sulfate. Chondroitin 6 sulfate can be a similar one. Here we will find simply N-acetyl D-galactosamine 6 sulfate. Instead of it was the earlier one was 4 sulfate, here it will be 6 sulfate. And next one is hyaluronate. Next one is the hyaluronate, which is a very common thing in connective tissue, In this semester, you will be studying also the this one. So here you will find N-glucuronate and N-acetyl D-glucosamine. Very simple. There is no structural complexity at all here. Only one thing is that here the linkage is beta 1,3. This is beta 1,3 and the other one was beta 1,4. So when we will have another N-acetyl glucosamine, so this linkage is beta 1,4. So this is the hyaluronic acid. So with this we came to what our time is up. We will be now in the next class we will be studying about the dermatan sulfate, keratan sulfate, and of course a very complex structure about the murine plus few other glycoconjugate. So this much for today. Thank you very much.